Good afternoon. Good afternoon, ladies and gentlemen. So, I thought I picked a pretty good year when I was deciding to do this project. It turned out, it doesn't always work out that way, but I'm glad that I did this project when I was looking at where their water came, where they were taking up water in 2023. It turned out to be quite the year. Of course, when we think about what was really, why I was really interested in looking at water uptake was mainly because I'm interested in roots and trying to figure out what roots are doing. If you think about roots, one of the important part about roots is they're essentially you can look at them as the supply chain of the plant. They're the ones responsible for taking up basically all the nutrients and water for the plant. And water, we don't normally consider it a nutrient. In the end, it is the largest substance that they are taking up through roots. I calculate about 9,000 gallons are transpired through sugarcane leaves per every ton of harvested cane. So a lot of water. You think about if you're going to figure out where they're taking up water, we just look at where the roots are, and that'll tell us where they're getting their water from. And that doesn't actually happen. It's not like that because roots have different functions. And so there's some roots that are actually more for nutrient uptake, and others that are more for water uptake. And so, yeah, root presence doesn't necessarily tell us what roots are doing. And you can see that when you look at what I call the classic, the classic root system. This is a sugarcane. You see there's the different, see if I can, is there a, pointer options. Can you see that? Yeah. Okay, that's better. Okay, so there's basically different types of roots in a sugarcane root system. You have first, we can look at these lateral roots. They're fine. They're shallow. They're only in the superficial soil. They have normally very small diameters, very low flow rates. Then they have the crown roots that are coming off of the root crown. These crown roots are coming down, and they normally are dropping vertically in the soil and go to deeper depths. And then there are rope roots. These don't occur in all varieties, but they are almost cord-like root system that has been found as deep as 6 meters. You're talking, almost 20 feet deep. And one of the things that was motivating doing this project is I was looking at, okay, this is the classic root system, but is it ideal? If we're talking about trying to find out what the ideal plan is, do we need all those roots? You think about it, roots are expensive to make. It requires a lot of photosynthase to not only keep them alive, but also for their construction. Do we need? Is this what we actually need, or is there a modified root system would actually be better? And this is, for instance, we have all the deep roots here. Are those necessary in Louisiana? Louisiana is pretty wet. Do we actually need deep roots? That could be a place if we, for instance, if we bred for sugarcane with a smaller root system that can still take up the nutrients and water necessary for production. More of the carbon that is assimilated in photosynthesis could go to sugar production. So given a reason why you kind of look at different allocations of carbon, why you'd be actually maybe interested in having a smaller root system if we can get by with that. And then as part of that is two of these lateral roots. Why can't they are they just for nutrient uptake? Typically, the lateral roots are classically considered nutrient, their principal role is nutrient uptake. And, well, can they take up enough water? Are they able to support the sugarcane for water uptake as well? So these are some of the ideas that I was thinking of when I decided to do this project. And how I was able to do this project was take advantage of the fact that there are stable isotopes of oxygen and hydrogen in water, and that we can use as a natural tracer of sugarcane water source use. And that's because, if you go back to a little bit of chemistry here, there's a stable isotope, there's a light and heavy isotope of each of hydrogen and oxygen, just to show kind of how that, so in oxygen, you have oxygen 16, which is 99.8% of all the oxygen found in water, and 0.2% is the heavy isotope, which is oxygen 18. Remember, these are stable isotopes. This isn't radioactive isotopes. This isn't anything. This is things that are found naturally in the environment. We're just taking advantage of what's already found there naturally. Like, for instance, everyone here has water in their body. Part of it's oxygen 18, part of it's has oxygen 18, part of it has oxygen 16. It's just natural. And what we can do, the reason why we can take advantage of stable isotopes is, even though they're chemically the same, they have physical, they are actually different physically, and we can take advantage of different natural processes that fractionate we call fractionate, or change the ratio of oxygen 18 to oxygen 16. So how much oxygen 18 there is in, for instance, a water pool relative to how much oxygen 18 there is relative to oxygen 16. And one of those processes is evaporation. Now, this is a project, I mean, if you ever want to see if this is actually, to understand this, you can actually do this at home. If you get a big old vat of water, measure the density of that water, and then allow it to evaporate down to where there's just a little bit of water left, like right here, and then measure the density of that water again. That water will actually be heavier than it was originally. And the reason being is that water with oxygen 16 evaporates at a faster rate than water with oxygen 18. And so over time, there will be what we call an enrichment that takes place in the remaining water. We can take advantage of this in natural situations. So for instance, this is a graph. Along the x-axis here is the isotop composition of water in the soil, and this is just soil depth. Imagine if you had a rainstorm. Rains, that rainstorm, water has a certain isotope composition. It fills up the entire soil profile with water of all the same isotope composition. And then what happens is you have evaporation, right? And water starts to evaporate. Of course, it's going to evaporate more from the shallow soil than the deeper soil, and so that water is going to become enriched. It's going to start to have more oxygen 18 relative to oxygen 16 than it had originally, when it first rained. And you're going to see that the amount of enrichment that takes place is going to decrease with depth, and so you're going to get a nice isotopic gradient with soil depth. Now, to show how that would look in a schematic, imagine if you had different soil layers, where the most enriched soil here is at the surface, and then it gets less enriched and as you go down. And so then you can look at if each soil layer has a different isotopic composition. Now, how we can take advantage of that is, if we collect, what we can do is we can actually take soil cores, and we can actually collect the soil water from each of those different depths and compare that to the water in the root crown. And the thing that's interesting about the root crown, that water in the root crown faithfully records the isotopically the source, its soil water sources. So it basically tells us where in the soil it's taking its water. And this is a pretty nice little system where we can then determine at what depth the plants are taking up water. Okay. Just to show you some of the experiment we did, I picked 3 different sites. We have a heavy land, a sandy land site, and then a mini rhizotron. That's why I have some more root experiments there, and that's kind of as far as soil texture, it's in between the heavy land and the sandy land. We made measurements in May, July, August, and early October. The first 2 collections were down to 35 inches, and I decided we better go deeper, and so we went down to 80 inches. And there were 8 varieties. We collected root crowns from 8 different varieties. And at the mini rhizotron site, there were 6 varieties. And I bring that up because even though I can do a lot of these isotopic work in-house, the root crown water, unfortunately, I can't measure in-house, and so I had to set it out. And it's taken a lot longer than expected to be able to analyze all that data. So I only have part of it back. And I'll focus now just on what I found at the mini rhizotron site so far. But just to show a little bit, this, of course, I've already seen a little bit of this, and it's something people are very well aware of, that 2023 was a very dry year. At the farm, I mean, it definitely was, we had measured there was 35.5 inches of rain. This is when we had the collections, and so this number here is just how much rain up to that point of the year we had. So you can especially see if you look when we get to August, I think it'll rain like a little over 1.5 inches between July and August, between those two collection periods. So pretty dry. We can see that also is evident in these, and these are soil profiles. So on the y-axis is soil depth, on the x-axis is the amount of available water to plants. So this isn't the total water in the plant in the soil. This is what water that is available for plant water, plant uptake. So, and I want to just kind of focus a little bit. If you look right here, this is the yellow line here is the is May, what the soil profile looks like in May. You can see that it is it's the time when there was definitely more water available. It was already still kind of dry in May, but there was definitely more available water in May than there was later on the year. And you see in the green in July, and it's already, there's a progressive drying. You can see it's drying out, and even more in August and October, when a lot of the available water in the shallow soil is gone. But yet deep, there's still water available, especially when you get closer to the capillary fringe. And that was, of course, worse in the heavy land of all the sites. That's where they really saw a lack of available water. When we look at the isotop gradients in the soil water, we see a nice, couldn't ask for better than this as far as isotopically, is that there was a nice gradient with soil depth isotopically. That makes a lot, being able to use isotopes makes it a lot easier when it's well defined. And so now I'll just show you, and we're going to focus on interdry because that's where I have data so far. But I want to show just one thing. It was first interesting when I got the results back. I had the 6 varieties, and I was expecting most likely there wouldn't be any differences, but I was actually quite pleased to see that there was, that the 6 varieties broke into 3 groups. The first group, and the shallowest group, was HO 17776 and HOCP 96540, where 776 is a parent variety. Of course, this is a commercial variety, and they took water from about 20 to 28 inches down. That was the shallowest, and if you think about it, that's actually quite deep. That's getting down into below the row and that's where they're starting to take up water. The next group was 299, 885. Also, they were even going deeper, 28 to 35 inches. So we're getting down pretty deep in the soil profile with, where they're taking up water. And then the last group was one of Dr. Hill's varieties, energy cane varieties, AFRI 15.8 and then 113, both energy cane, and they were taken below 35 inches, so even going deeper. And so we see that all these varieties, even though this is the time of the year when water would be most available in 2023, they were all going deep from the beginning. And like I said, I can't wait till I get the rest of the data to look at this, but I have a feeling that it's going to be probably more of the same. I have a feeling they're going to be all showing the same thing, that they're going deep, and probably even, and I'm curious if they'll even show going deeper than 35 centimeters in these different varieties, as they try to, basically trying to chase the drying front in the soil. So just in conclusions, asked the question at the beginning was, is it necessary to have, are deep roots necessary? And I'll tell you, in 2023, they certainly were. If there weren't deep roots in sugarcane, it would have looked a lot different in 2023. At the farm, yields in 2023 were a little above 2022 yields. Yet if we didn't have deep roots, I can tell you it wouldn't even been anywhere near that. Also, another thing to also remember, it doesn't mean that because we have deep roots, it's important to have a lot of deep roots. It's not necessarily the case. A lot of times only a few roots can be able to take up enough water to support the plant. A lot of times those roots that go deep are a larger diameter, they have larger vessels, and so if you look at the physics of flow, large diameter roots can move a lot more water than a lot of fine roots. And so there's been cases with other studies I've seen where less than 20% of the roots go deep, and yet they account for basically all the water uptake. And that's probably the case with sugarcane as well. It's just a few roots they drop down that basically keep that plant alive when we have, when there's not, basically throughout the summer when it's dry. Also, the other part, superficial lateral roots, where it doesn't look like they were taking up water. Isotopically, they weren't. It looks like they're probably mostly responsible for nutrient uptake. And I'm curious, I'm going to do the study again this year to see if, I assume this is going to be a wetter year. It's turned out to be a wetter year than last year. So we'll see what happens in a wet year, how the story is the same or if it's different. But as of a dry year, those roots are not ones that are taking up water. And then the last result that I was really happy to see was that we have variation across cultivars. There is variation in rooting depth, and that's important when we get to the point where we can start to select for different traits such as root traits in the breeding program. That would be interesting to look at, find that ideal root system, what we need to actually be selecting for, and looking at actually modification of the rooting architecture. And in particular, being that the energy cane were the ones that had the deeper root systems, we've gone to spontaneum a lot to introduce new genes and traits to improve sugarcane varieties, and it looks like that will probably be a good source also to introduce, if we get to that point, to introduce new rooting traits as well to our modern sugarcane varieties. And with that, I'd like to just acknowledge funding sources was the American Sugarcane League and, of course, ARS. And then I'd like to thank my Lab Tech Dallas, who did a lot of this work, and WSU, Washington State University, is running my root can samples. But with that, I'd like to take any questions. Yes. Yeah, you can, and there's, when you look at that, and there's natural systems that are like foggy, that are arid, but are like, for instance, along the Chilean shore where there's basically zero water, but they basically rely on fog, right? That's hitting the leaves, missing the leaves, and that uptake. But when you deal with a situation like that, you're talking about very small amounts of water. And so to keep those alive, to keep plants alive, you either have a very arid situation where that occurs, or you have a situation where we just heard about VPD, the amount of water that amount of evaporation that can take place. You must have a very, very low evaporative potential. That must, you're dealing with 100% humidity all the time to be able to, where the plant can survive on such a small amount of water, because they just can't take up that much. We're talking about thousands of gallons. You just can't get that through any other way than root systems. And give an example of that. One of they found some of the trees in the redwood forest. They found that's a major source is mist. But what happens? That mist actually collects on the leaves, drops to the soil, and the plant takes it up. And because that's the more efficient way, more effective way of taking the water in. Any more questions? Yes, Todd, James. I'm curious. I would say probably I probably can see a lot more shallow water to uptake, just because the issue you have with depth is you think, well, why don't you just go deep all the time? It's the guaranteed source. So if you look at how much, you think about a straw and how if you're sucking out of a straw, because remember plants are dealing in a sense is almost like suction is how they're taking water up. the size of that straw makes a difference. If you have a really long straw, you're going to have to suck real hard to get water up. And so the same with the plant. The deeper the source, the more suction that takes place for that water to come up. And so you're not going to have as high of water movement. And so if you have two sources, one being shallow, one being deep, and there's roots in both of them, you're going to see a preferential uptake from the ones that are shallow. The difference being, and this one I don't know, is the roots at the shallow roots are extremely fine. So the root diameter is extremely low, and so is the vessel diameter. And small vessels, if you look you look at the flow through basically a tube, the flow is to the fourth power of the radius of the tube, and so small increases in diameter can cause huge differences in flow. And so those small roots, you're going to have them all. It'd take a huge amount to be able to take up the same amount of water as a few bigger roots. So I don't know for sure. That's where we're going to have to do it again this year to see how it looks in a wetter year. Oh, wait. Herman, one more question from Herman.
Is there any kind of evidence that we select for more efficient varieties over the years? Is that, would you be able to do some type of study?
I haven't looked at enough to be able to answer that, enough varieties to get at that question. The fact that even among a small group, we have variation, tells me that probably not. It's probably not being directly selected in anything that we're doing.